robot has made significant stride, offering an excellent adaptability. However, we still find it challenging to develop certain robot types for real-time applications. Good afternoon, everyone. I'm Dulanjana Pereira, here today to present our paper on curve-parametric modeling of soft plane robot. Soft plane robots are crucial due to their natural compliance, which allows them to interact safely and effectively in environments that rigid robots cannot. Their adaptability to cover space and form complicated shapes makes them ideal for applications like locomotion, manipulation, and altering system characteristics in real time, such as changing the shape of the airplane wing. Our work here is motivated by the need to develop fast and accurate shape estimation method that will enhance the practicality of planar robots in real-world application. Only a few studies were conducted to model the surface of soft planar robots. Here we have outlined most prominent studies. The first approach shown here utilized lump mass approximation combined with Lagrangian modeling, which incorporate both internal and external dynamics. This method is quite accurate in estimating the shape of the robot. However, it is limited to use of two actuators and does not provide details about algorithm's efficiency in terms of computational time. The second one, it used modified continuous pseudo-rigid body modeling method that has been proposed to estimate the shape, and they interpolate the curvature at the middle. That's how they obtain the surface. It's only focused on the kinematics. While this approach can model the movement of the robot, it lacks accuracy and, similar to the previous method, does not address the efficiency or time requirement for the computation. In the third study, a curvature derivative control approach combined with continuous Newtonian mechanics is utilized to get the model. Primarily, it focused on locomotion rather than shape estimation. However, this study is limited to simulation without providing real-world validation. The fourth study employs Lagrangian mechanics for modeling and offers both inverse and forward shape estimations. However, while it shows maximum error of 20% in concave shapes, it does not provide data on efficiency of the approach. Therefore, there's a need for efficient model for real-time applications, and we propose a curve-parametric method to model the planar robot's shape. The outline of the presentation is as follows. First, I will present our contribution to this study, then the prototype design and the system characterization. After that, the system kinematics will be presented as well as the surface modeling approach. Finally, the experimental validation of the proposed model and the conclusion of our work will be presented. The contribution of our work. We develop a soft planar robot with modular capabilities that can be arranged in a matrix for more complicated shapes and tasks. And the second contribution is we develop a constant curvature based forward kinematic model. And then we also propose a Bezier surface modeling approach to estimate the surface of our design. Finally, we experimentally validated the proposed model. Let's see the prototype design. The base of our planar robot is constructed from non-stretchable fabric, which ensures that muscle bending maintains constant curvature. Pneumatic muscle actuators are used as actuation mechanism, arranged in a square shape to achieve symmetricity. This PMS extends when pressure is applied, and the antagonistic muscle arrangement allows for bidirectional planar bending. We use 3D printed mounts to anchor the PMS securely with the pocket to keep them in place. This is the pocket we put our PMA inside the actuator. Additionally, the rubber joints are included to provide necessary structural rigidity while is allowing for flexible movement. The characterization of the system. We conduct an experiment to determine the relationship between actuator space and the joint space. To map the extension versus pressure, we average the result of 5 trials. Here, P represents the pressure applied and L indicates the absolute extension. A fourth order polynomial was fitted to their data, and the resulting plot revealed that the PMA has 0.5 bar dead zone. When pressure is applied to the system, it creates unbalanced moment that causes robot to bend, as shown in this figure. We model the neutral line of the planar robot using a constant curvature approach, which allows us to map both configuration space and joint space. In this model, phi represents the bending angle, r indicates the height of the neutral plane. However, it is important to note that our study we do not utilize these maps directly in the kinematics. Kinematics of the system. First, we derive a coordinate kinematic for a single antagonistic muscle set. We use coordinate transformation method to determine the forward kinematics of antagonistic muscle set, especially referring to this frame. It involves moving the frame along the radius through the center to the tip. By applying this method, all four models can be derived and integrated into the complete kinematics for ease of analysis. The psi here serves as a selection factor ranging 0 to 1, and 1 represents the tip of the PMA. Our robot can be considered as a 4-bar mechanism exhibiting closed loop kinematic. To model this, we utilize kinematic chain approach, which allows us to fully capture the robot's movement. By applying coordinate transformation, obtain forward kinematic at joint 3 from both directions. For simplicity, the equation represented earlier used as a single antagonistic muscle set transformation, ensuring clarity of the model presentation. The angle alpha in the kinematics denotes the rotation of the joint or antagonistic muscle set around its longitudinal axis. This allows us to model actual surface deformation that we observed during the preliminary examination. In order to solve the kinematics, then we utilize optimization to solve the alpha, which is unknown in the system. The cost function is crafted using the position vector of the joint tree from both directions. The constraint optimization allows us to obtain the realistic forward model. We limit the search for the alpha for minus pi by 2 and to 5 by 2 gives us the actual deformation of the robot. The complete kinematics of the joint can be presented as this. The alpha star is the result of the optimization, and psi is the selection factor which selects the joint of the robot, but we can select any point on the surface of the robot. Surface modeling. We use the forward model to derive the kinematics of the constant curvature arc of PMA. Then a cubic Bezier curve is carefully fitted to this arc. In order to do that, least square fit approach is used to find out the control point, especially B1 and B2. We crafted the error function for least square fit. The error represents the square of error between arc and the Bezier curve. We use boundary conditions B0 and B3 and the error gradient to find out the control error gradient of B1 and B2 to find out this remaining control point. Once edge control points are obtained, we perform a weighted average to get the middle control points. This provides us a surface control points need to generate the Bezier patch like this. This represents all the intermediate control points obtained through weighted average control points. The Bezier curve along x and y are used to generate the surface. Here Cx and Cy denotes the control point index along x and y direction axis. This approach facilitates us to generate surface that has two different varying curvature along x and y. Experimental validation, and this side outlines the experimentation experimental setup we used. The pressure was controlled using SMC pneumatic valves, which allow us precise manipulation of the actuation, and motion tracking system monitored the markers on the surface of the robot, while IMU attached at each joint provide real-time bending angle data. This is a demonstration of showcases the actuation of planar robot, and the red color marker here you see represent the robot coordinate frame. We have strategically placed IMUs at each joint to measure the pi angle of each pneumatic muscle actuator. Slide shows the experiment model accuracy of convex bending of a single antagonistic muscle set. The results are presented in a later slide, but I want to point out that middle form that does not affect the actuation is to illustrate the surface deformation. Similar experiment results are presented in this slide. This is a negative bending, which is known as concave bending of surfaces. The error is calculated for the length of the PMA, and a plot depicts a maximum error percentage was observed at joint 4, which is 12%. That means approximately 1.5 centimeter offset from the actual robot. The multiple bending is demonstrated in this figure. Results indicate that the model finds challenges when multiple antagonistic muscle sets are actuated together. The observed error percentage here is 20%, which is 3 centimeter for 17 centimeter long actuator. This is mainly due to the internal dynamics that are not accounted for the kinematics model. This is just a showcase for mixed bending. Here we don't evaluate quantitatively, but to demonstrate the proposed robot capabilities that can demonstrate mixed shape bending. Finally, the conclusion of our work, the arrangement of 4 antagonistic muscles can deliver convex, concave, and mixed shapes effectively. The proposed model can estimate the shape of the robot with 12% body length error, but a mixed shape generates approximately 20% of error. Algorithm can estimate shapes with 30 Hz, which is significant for real-time controlling. In future, we are planning to propose an efficient dynamic model to improve the multi-bending and mixed bending accuracy of the system. And thank you so much for listening and nominating our work for Best Paper Finalist.